all. Good morning, bro.
Okay, thank you. I've already informed you that I've uploaded your first group assignment in the e-learning. I hope you have no problem uh, in choosing a group, choosing your partners for your group. Okay, so okay, let's see what we have discussed last week. I've already introduced you this concept of partial derivatives, right? Partial derivatives, and we have looked at some examples related to partial derivatives. Any question regarding our lecture last week? We have also looked at some applications of chain rule. Yeah. Okay, you have your first assignment. I've already uploaded in the e-learning. It's due this coming Thursday. Yeah? Latest Thursday means what? Until what time? Until 11:59 p.m. Okay. You have until on Thursday. You have until 11:59 p.m. To submit your first assignment here. I haven't created the portal yet in the e-learning. I will create the portal for the submission of your group assignments. Yeah. Okay. Any questions first regarding the partial derivatives that we discussed last week? So far, we have only looked at partial derivatives of function of two variables. Huh? Two variables. Okay. Um, the idea can be extended also to partial derivatives of more than two variables. Yeah. 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 If g, x, y, z is a function of three variables, then here we can calculate three first partial derivatives: g partial x. G partial x means we should regard the variable y and z as constants. G partial y means we differentiate only with respect to y, holding x and z are constants. G partial z means we differentiate with respect to z only, holding the variables y and x as constants. Yeah? So let's look at some example of that. Wonder why I cannot write anything. Why I cannot write anything on the screen using my electronic pen? I wonder. Let me close this apps. Then try again. What happened now? I'm not able to write anything on the Something is not right. Okay. For an example, suppose we are given a g, x, y, z equal to e to the power of 2x cosh of z plus e to the power of 3y. We have here, suppose, sine of z. Okay, cosh of z is a hyperbolic function, right? So here we have an example of a function of three variables, x and y, z. So what is g partial x? That means we want to differentiate this function g with respect to x, holding z and y constant. So only the first term contains x, so the derivative of e to the power partial of 2x is 2, right? 2 e to the power of 2x cosh of z plus 0. Because the second term has no variable x. And since we are treating y and z as constants, so when we differentiate the second term with respect to x, it is 0. Right? So this is 2e to the power of 2x cosh of z. Okay, next, what is g partial x partial y this time? Anybody want to try? Can anybody tell me what is g partial y?
0 plus 3e and 3 exponential power of 3y.
Plus 3e
power 3y.
3y
Sine
times
z.
sine z, right? Yes. So this time, the first term, this time we are going to treat x and z as constants, right? So the first term is independent of y. So the derivative of the first term with respect to y is 0. Yeah. So the answer is 3e to the power of 3y sine z. Okay, a third first partial derivatives is g with respect to z. Anybody else who wish to try? One Ashraf, Danish. Yes.
Exponential 2x sine hyperbolic
Exponential.
of z
Okay.
plus
Mm-hmm.
exponential 3y cos of z.
Cos of z, yes. So this is e to the 2x times shin, z plus e to the power of 3y cosine z. Okay. So for g partial z, we treat x and y as constants. So the derivative of cos is shin and the derivative of sine is cosine. All right. So of course this can be extended to functions of 4 and higher variables. Okay. Now let's look at higher partial derivatives. So far we have been looking at only first partials. If z is x f x partial y, then we have looked at z partial x and z partial y. Okay, for z function of x and y. So just like in calculus 1, derivatives, right? First order derivatives, third order derivatives. So similar ideas can also be applied to partial derivatives. For example, the first symbol here. The first symbol here is z partial x partial x. Subscript x and x. Okay, so it means that first we calculate f partial x, and then we differentiate again the result with respect to x. Okay, so it can also be written in this form. So this is called pure second partials here. We can also have mixed partials as shown in the next equation. Here we have z partial y partial x, or written in the form of this symbol here, f with subscript x y. It means that first we take f partial x and then differentiate the result with respect to y. Okay, it can also be rewritten in this form. So this is called mixed partial because we have partial with respect to x and partial with respect to y. And similarly, we have another mixed partial, f partial y partial x. Okay, as written in this notation here. So what this means, f partial y partial x, it means first we take f partial y and then we differentiate the result with respect to x, which can also be written in this notation here. Okay, so the order is important, right? The order is important. You see the difference between f partial x, f partial x partial y, and f partial y partial x. When we have x partial y, first we compute f partial x first, and then we take partial y, and then we take the derivative of the f partial x with respect to y. Okay. On the other hand, f partial y is partial x means takes f partial y first. Okay, we calculate f partial y first, and then we take f partial x, and then we take partial x for f partial y. And also we have another possible second partial derivative for f xy, which is f partial y partial y. Okay, so these are called if second order partial derivatives here. So let's look at some example here. suppose we are given this function here, y. See what we have calculated before in the previous lecture notes. We have calculated several first partial derivatives. Okay, let's okay, this is what we have calculated before, the first partial derivatives. So what is z f partial x? Suppose now I want to calculate f partial x. We have found f partial x, so what is f partial x? Partial x.
4.
4, right? Yeah, so it means that we want to find the partial derivatives of 4x minus 3y cubed plus 7, so the answer is 4. What about f partial x partial y?
Uh, 4x negative 9y squared.
No. Okay, it means what? It means we want to calculate the partial derivative of f partial x with respect to y. Okay. So try again.
Negative 9.
Negative 9y squared.
Y squared, yes. Okay, what about f partial y partial x? This means that we want to calculate the partial derivative of f partial y with respect to x. We have found earlier f partial y is minus 9 xy squared minus 6. So what is that? It's minus 9 y squared, right? That is the answer. Minus 9 y
Minus
squared.
9 y squared.
Yes, yes. And then we have another second order partials is f partial y. So this means that we want to calculate want to differentiate f partial y with respect to y. What is the answer here? Minus 18
x y.
x minus 18
xy.
xy. Yes, minus 18 xy. Okay. So it's clear, isn't it, how to take second order partials here. And notice here that f partial x partial y is the same, right, as f partial y partial x. Notice that the mixed partial f partial x partial y is the same as f partial y partial x, isn't it? They are equal, right? They are equal. So that is true in general, provided a certain condition is satisfied. Yes, the equality of mixed partials. Let fxy be defined on a domain D if f partial x partial y and f partial y partial x exist at each point of D and are continuous. Okay, this at a point AB, then they are equal. Then the mixed partials there are equal. So this is important condition for the continuity here. Okay, so this that the both mixed partials are continuous. Yeah, then only we can have this equality of mixed partials here. So this is already proven in mathematics. What does it mean that a function fxy is continuous? In mathematics, continuity of fxy at the point AB means f at the point AB is defined. Okay, say it is equal to L, and the limit of fxy as xy approaches AB exists. Say it is equal to M. And if L is equal to M, then only we can conclude that fxy is continuous. So this is something, related to mathematics. Yeah, it is this is not discussed in this course. This concept of continuity is, however, not discussed in detail here for this course, in this course, but it is discussed in detail in the mathematics course. Yeah. So I mean so actually in mathematics, these mixed partials, they are equal provided this continuity condition is satisfied. Yeah. So you can see here both functions minus both see minus 9y squared. See f partial x partial y is continuous function. F partial y partial x is also a continuous function. So because the continuity condition is satisfied, so we have this equality of the mixed partials here. Okay. And we can also calculate higher, not just second order. We can also calculate third order. For example, what is f partial y? If I continue, suppose I want to calculate f partial x partial y. What is it? That means we want to find the partial derivative of f partial y partial x to y. So we have already obtained f partial y partial x above, which is minus 9y squared. So the answer is minus 18y. Okay. Yes. I now ask what is f partial y partial x? Yes.
Negative 18y.
Negative 18y. Yes. Negative 18y. And what is f partial y now?
Negative 18x.
Yes, negative 18x. Okay, hope you have grasped of this high. Partial derivatives are very important in applied mathematics. Okay, let's look at this example that we have just worked out just now. No. Okay, let's take this our next example. Okay, we have looked at this example. G is a function. See, we can also we have calculated the first partials here. Okay, so similarly, we can also calculate second partials for these functions. What is G partial X partial Y? Yes. What is G partial X partial Y here? Means that we want to calculate the partial derivative with respect to Y to the function G partial X. And this is G partial X. So what is it?
0. 0.
0, yeah, because there is no Y here, right? There is no Y in G partial X. There is no Y. So equal to 0. What about G partial Z partial X? Suppose I now ask, what is G partial Z partial X? What does it mean? We want to calculate the partial derivative of G partial Z with respect to X. So this is G partial Z that we have calculated just now. The partial was the derivative of G partial Z with respect to X. It's 2, right? 2 e to the power of 2x shin Z, right? Shin Z. And the second term is independent of X, so it is 0. So this is the answer. So what is G partial Z partial Z partial Z? We have already calculated G partial Z. So we need to find G partial Z first. Right? So we can also write this as G partial Z. The second partial derivatives of Z with respect to Z. Yeah. So we have already obtained G partial Z. So it means that we want to calculate It's G partial Z. Yeah, e to the 2x shin Z plus e to the power of 3y cosine Z. So we calculate G partial Z with respect, we differentiate G partial Z with respect to Z once. The result is e to the 2x cosh Z, right? Cosh Z, then minus e to the power of 3y sine Z. So that is, this is the same as G partial Z partial Z. So differentiate the result once more with respect to Z. The answer is e to the Z shin. This is x. Shin Z minus e to the power of 3y cosine Z. Okay, that is the result. So, okay, are there any questions regarding the higher order partial derivatives? All right, so partial derivatives are very important in applied mathematics and engineering. There are many applications, many physical phenomena can be described using partial differential equations. Yeah. So one example is the Laplace equation here. Yeah, this one here. The harmonic functions. A real valued function phi xy that satisfies this equation below here. Right? It's said it's called a harmonic. Yeah, it's harmonic. This equation here is called a Laplace equation here. See, this is in the form of second partials, right? Yeah, and phi xy is a function of two variables, and this is called the Laplace equations here. Has a continuous first and second partial derivatives in domain D. Such a function is called a Laplace is called a harmonic function here. This is named after the French mathematician Laplace. So this is a very important equation. It's called Laplace equation. For example, we have a Dirichlet problem. A Dirichlet problem is the problem of finding a function phi xy such that it is harmonic in the region D, and then it has a boundary data. On the boundary gamma, it satisfies a function phi naught. So this is called a boundary data here, and this is called a Dirichlet problem. See, many problems, physical problem, can be described in terms of Dirichlet problem. Yeah. And then we also have what is called the Neumann problem. It is the problem of finding a harmonic function phi in the region D, where on the boundary gamma it satisfies this the normal derivative. The normal derivative equal to some function phi naught. This is called a normal derivative. We will study this later on. Okay, about normal derivative here. So it's called Neumann problem. There is another problem called the Robin problem in applied mathematics. So a problem of finding a function phi which is harmonic in the region D, where on the boundary gamma it satisfies a linear combination of the Dirichlet and the this is called Robin condition. It's a linear combination of Dirichlet condition and Neumann condition here. So there are many problems, that can be described in terms of partial differential equation here. Let me show some example here. Show that phi xy equal to x cubed minus 10 x cubed y squared plus 5x y to the 4 is harmonic. Okay. So that means we want to show that this function phi satisfies the Laplace equation. Okay, so we want to show that phi partial x plus phi partial y equal to 0. So first we calculate phi partial x. Phi partial x is 3x squared minus 30 x squared y squared plus 5y to the power of 4, right? And what is phi partial x? We differentiate phi partial x with respect to x again. We get 6x. What else? Minus 60 xy squared, isn't it? Yeah. Next, we compute phi partial y. Phi partial y is minus 20 x cubed y plus 20 xy cubed, isn't it? So therefore, phi partial y is minus, am I right?
20x cubed.
Huh?
Minus 20x cubed plus
I'm sorry, I made a mistake. This should be x partial 5 actually. This should be x partial 5 actually. So need some correction. Should be here what? 5 x partial 4, right?
5x partial 4, yes.
And this one should be 20x cubed.
20x cubed.
20x cubed, okay. So phi partial y is, what is phi? Phi partial y is correct. What is phi partial y? It's minus, right? Minus 20x cubed
Minus 20x cubed plus 60x
xy squared, isn't it?
power of 2, yes.
So So now if we add up phi partial x, phi partial y, is equal to 0, isn't it? If you add them up, phi partial x with phi partial y is equal to 0, right? So therefore, phi is harmonic, right? Yeah, therefore phi is a harmonic function here. Okay, let's do one more example. Show that say f xy equal to the inverse tangent. You have already studied inverse trigonometric function, right? So the inverse tangent y over x is also harmonic. Yes. So in calculus, recall what if y equal to the inverse tangent of x, what is dy dx? It's 1 over 1 plus x squared, right? Yeah.
Yes, sir.
So so in this problem, you want to show you need to recall this basic formula. This is a basic formula that we want to work on later on, that we want to apply. So we want to show f is harmonic. That means we want to show that f partial x plus f partial y equal to 0, right? Yeah. So what is f partial x, for example? You have to apply the chain rule here. Apply the chain rule. It is 1 over 1 plus y over x squared, and then times the partial derivative of y over x, right? Yeah, this is what you need to calculate. Using the chain rule. And so here we have 1 over 1 plus y squared over x squared. What is that partial? This is equal to y x minus 1. It's like we want to differentiate x to the power minus 1. So it is minus 1 over x squared, right? Yeah. So if you multiply x squared to the other denominator, you will get x squared plus y squared. So what is now f partial x? We differentiate again. We differentiate f partial x with respect to x. Yeah. So this, we can think of this like minus y times x squared plus y squared, or minus 1. So differentiate f partial x with respect to x, taking y as a constant. So we get y. Okay, using the chain rule again. The outer function is the power function, and then we differentiate the inner function with respect to x. We get 2x. So this is 2xy divided by x squared plus y squared to the power of 2 here. Next, we calculate f partial y. Again, using the chain rule, we will get this result. Then we want to differentiate y over x with respect to y. That is easy. So that is easy, right? So we have 1 over 1 plus y over x squared times y, just y, isn't it? It's just y. No. with respect to y. It's just 1 over x. Yeah, it's just 1 over x, right? So what is f partial y partial y? We can think of this as 1 over x times 1 plus y squared over x squared to the power of minus 2. So the outer function is the power function, so we get minus 2 times 1 plus y squared over x squared to the power of minus 3, isn't it? Minus 3, then we differentiate the inner function with respect to y, so we get 2y over x squared. So what is this thing equal to? I'm sorry, this is minus 1, not minus 2. Oh, yeah. How come nobody corrected me? So this is minus, dear, minus 2 here. So what is the result here? We have, yeah, 2y, that is correct, yeah, that is correct, yeah. This is minus. So let's simplify this. This is the same as 2y over x cubed times 1 over 1 plus 1 over y squared over x squared to the power of 2. Can we simplify that? What do we get if we simplify that?
After the negative symbol,
Negative sign.
So y
You
over
don't know the
negative sign.
negative sign.
oh yeah, there's a minus sign there. That's right.
Minus, yes. Okay.
Minus. Thank you very much. The next expression can be written as x to the power of 4 over x squared plus y squared squared, isn't it? So this simplifies to minus 2xy divided by x squared plus y squared squared. So okay, you see, so when we add up f partial x with f partial y, the terms cancel out, right? So it is equal to 0. Yeah. So this implies f is harmonic. Okay. Any question for this example?
Doctor,
Yes.
how come the x power of 4? X to the power of 4.
Okay.
Is it?
You see this
Bukan
one
satu
here?
ke? Oh,
You see this one? This can be written as 1 over x squared plus y squared over x squared squared, right?
yes.
So that's why it is equal to that one, x to the power of 4. Okay. Yeah.
Okay, understand.
This is just algebra. It is just algebra work. Yeah.
Tak perasan.
Okay. Yeah. So harmonic function is very important, in applied mathematics. Even in electrostatic, it can give rise to harmonic function here. Okay, this is what is called electrostatic. Yeah, the electric field intensity, capital, is a vector valued function. You will study this in detail later on about vector calculus, vector valued functions. But for now, let's just go through this simple explanation. This electric field intensity f, which is a vector. It's a vector valued function due to a collection of stationary charges in the region of the plane is given by. I think we take a 10 minutes break. Huh? All right. Let's take a 10 minutes break. Yeah. Because you told me you want a 10 minutes break. So let's have a 10 minutes break here. Okay, let me show you some other applications of partial derivatives in science and engineering. So one of the problem is related to electrostatic here. Okay. So we have this electric field. It's called a vector field actually, which can be represented in terms of minus. This is a gradient symbol here. Okay, you will study this later on. Where phi is a electrostatic potential. Yeah. So we have an electric field written in terms of a gradient of a function phi. So phi is a function of two variables here, electrostatic potential. Yeah. It can be shown here using some laws of physics. It can be shown that phi satisfies a Laplace equation here. These are some vector calculus notations here, which I will discuss with you sometimes later. But what I want to show you is that it leads to a Laplace equation. So phi is a harmonic function. So phi here is called the electrostatic potential. And it can be shown that complex potential here, yeah. So if phi is a electrostatic potential, we can determine another function, psi here, which is called the stream function. Okay, and this and the level curves. Okay, remember last time we discussed level curves for function of two variables, level curves for function of three variables. So the level curves, okay, phi equal to constant. These are called the equipotential curve. And psi equal to, this is a function psi equal to constant d. These are called streamlines. Okay, these are called stream function here. And they can be proven they are mutually orthogonal. It means their level curves intersect each other at right angles here. So with that property, okay, if we think of if this object is at a higher potential or higher voltage than this object, which is at a lower voltage, then charged particles would move, isn't it, from higher voltage to lower voltage, and this shows the path. Okay, the stream function equal the level curve psi equal to constant shows the path along which a charged particle will move in the electrostatic field here. And this we call equipotential curves. The electrostatic potential equal to constant k. These are called level curves. These are the level curve shows along which the potential is constant. Yeah, this a dotted curve here, a broken curve here. They refer to equipotential curves. So all points on this broken curve, points where they have the same potential, the same charge. Yeah. So this is one application of harmonic function. They can and harmonic function involves partial derivatives. Okay. Yeah. So this is important, or even in electric. You are in the electric engineering, isn't it? So I'm sure you will see this concept also when you study in your electric engineering courses. Yeah. So yeah, this table shows some physical interpretations of level curves. Yeah, level curves. So in the heat flow, okay, we have phi and psi again here. The level curves are phi equal to constant and the level curve psi equal to constant. In the heat flow problem, the level curve psi equal to constant is known as isothermals, while a psi equal to constant show the heat flow lines, how heat would flow from higher temperature to lower temperature. Yeah, and electrostatics, C equal to constant refer to equipotential curves. Okay, these are level curve where all they have the same voltage, same potential, while psi refers to flux lines. Okay, shows the path along how a charged particle would move from higher voltage to lower voltage. Yeah. In fluid flow, psi equal to constant is called equipotentials, and the fluid flow is called the streamlines. Okay, the streamlines. How water would flow. Yeah. And these are other interpretation as well in gravitational field, magnetism, diffusion, elasticity, and current flow. Yeah, current flow. This is in electricity, right? Electric current here. Yeah. So I will upload this information in the e-learning. Yeah. And there are other important partial differential equations as well, such as called the heat equation. Yeah. We have the temperature function uxt. Okay. Yeah. So suppose we have this. We have a metal bar of a fixed length, say from 0 to L. Okay, so we have so this metal bar has heat flowing along the metal bar. Okay, so this is the x-axis. X is from 0 to L, and T is a temperature, a time. Okay, so initially the initial, when T is 0, it is this is called the initial temperature distribution. Temperature distribution. Okay, yeah, when T is 0. And suppose we have boundary condition as well. Suppose U0T is equal to 0 degrees, and here the boundary condition at the end is also 0. Okay, and it can be shown that Ux satisfy a partial differential equation, which can be written as U partial x equal to 1 over K U partial T. So this is called the heat equation, where K is some physical constant here. Okay, so we want to determine how the temperature along the bar varies with time. So that problem can be described in terms of this partial differential equation here. Okay, this is called a partial differential. Just like we have ordinary differential equation, here we have a partial differential equation. So in other words, we want to solve this partial differential equation for u x t. Okay, so using this technique of Fourier series, it can be shown that the solution, this turns out it has infinitely many solutions. The solution can be written as e to the power of minus k n squared pi squared t over L squared times the sine function n pi x over L. Okay, yeah. There is a technique here, okay, to show that the solution of this heat equation is given by this function of two variables, x and t. Okay, the technique used is you need to have knowledge of using Fourier series. I believe you will take a course, okay, mathematics course in future that involves this special technique called the separation of variable methods, and then leads to this Fourier series. Yeah. Okay. And another example of application of partial derivatives is in the wave equation. Wave equation. The wave equation is say y xt. It's called the displacement y xt from the x-axis. Okay, satisfies. Remember, we have like a plug string. Remember, suppose we have a string here, right? Yeah, we have a string. Initially, suppose this is the position. This is the position. This is a string, something like string. Okay, the string lies along the line 0 to L. Okay, you pick one point along the string and you raise it up. Suppose this is the initial position. What is shown here is the initial position of the string. And then you release the string and it will vibrate, right? It will vibrate. Yeah. So how to determine the shape of the string at any particular time, at any particular point along this L? Okay, it can be shown that it satisfies this equation, this partial differential equation here. 1 over c squared y partial t partial t. Okay, this is called a wave equation here. So also written in terms of partial derivatives. Yeah, it can be shown that the solution can also be found with the help of Fourier series, that it has the form of y n xt equal to sine n pi x over L times this function a n cosine n pi c t over L plus some coefficient b n sine n pi c t over L. Okay, again based on the technique of Fourier series, using Fourier series. Okay, so this is another application of partial derivatives. Yeah. In electricity also, we have this example, the current represented here by I xt along a transmission. I got this information from calculus book, so I'm just giving it to you, this information. The current Ixt along a transmission line satisfies this partial differential equation here. Yeah. Plus RC I partial T equal to I partial X. Yeah, where R, L, C are constants. What is R in electricity? What is R normally? Can somebody tell me?
Resistor.
Resistance. Yeah, resistance. R refer to resistance, right? What about L in electricity?
Inductance.
Inductance. Yeah. And what about C?
Capacitance.
Capacitance. Yeah. Okay, so partial derivatives are very important in many problems of science, and engineering here. Yeah. Okay, let's continue with our lecture. Next, I want to discuss what is called the chain rule. The chain rule for partial derivatives. Yeah. Yeah, this one here. There are several chain rule for partial derivatives here. We have here z equal to fxy. And notice that x is in turns defined as a function of a single variable t, and y is also defined in terms of a single variable t. Yeah. Remember this for function of single variable, if the variable x is defined in terms of t, we call it as a parametric equation, right? Yeah. So here also we have a parametric representation of the function z equal to fxy. X is defined in terms of g as a function of t, and y is also defined in terms of a function of t. So x and y here, they are called parametric equations here. Then z as a whole is a function of t, isn't it? Z as a whole, z is a function of x and y, and x and y, they are both functions of t. So that means z as a whole is a function of t. So we can calculate dz dt. Okay. Here, look at the dz dt on the left. It is not written in terms of partial. It is written in terms of a straight d, not curly d. Okay. Because z is as a whole is a function of t, so that means we can calculate dz dt. And dz dt can be evaluated according to this chain rule here. Z partial x times dx dt plus z partial y times dy dt. Now notice this equation, there are some terms involving partial derivatives and there are some terms involving straight derivative here. Yeah. So, okay, let's see some example of that. This is there are other cases as well. Case A, case B, case C, and case D. Okay. Yeah. So let's look at this case by case. I cannot scroll this up and down. Oh yeah, okay. Suppose you are given this given z equal to e to the power of x squared minus e to the power of y over 2, where x is equal to t and y is equal to a function of t as well. Okay. So determine dz dt. Determine dz dt at t equal to minus 1 using partial derivatives. This is a sample test question. Yeah, this is a sample test question actually. So use the we use the formula given. What is the formula? Dz dt is equal to z partial x times dx dt plus z partial y times dy dt. Yeah. What is z partial x? Can anybody tell me what, given z here, what is z partial x? Yes?
2x exponential of x squared.
Yes. Yes, 2x times e to the power of x squared, right? The second term here, e to the power of y2, is independent of x. So if we treat y as a constant, so the derivative of the second term with respect to x is 0. And what is dx dt? Just 1, is it? You are given x equal to t, so dx dt is equal to 1. Okay, what about z partial y? Minus a half, right? E to the power of y over 2, isn't it? And dy dt is 3t squared minus 1. Yeah, so that is dz dt. And you can now replace x by in terms of t and also y in terms of t. So we get 2t e to the power of t squared minus a half e to the power of t cubed minus t over 2 times 3t squared minus 1. So that is dz dt. Okay. So the question also asks, what is dz dt at the point t equal to minus 1? So if you substitute this, you will get what? You will get minus 2e, then minus a half. Upstairs, what do we get? Minus 1 plus 1. So we get e to the power of 0, right? E to the power of 0 times 3 minus 1. So this is e to the power of 0 is 1. So we have minus 2e minus 1, which is, yeah, that's the answer. Minus 2 times a constant e minus 1. Alternatively, you can also derive when t equal to -1, we have x equal to what? We are given x equal to t, isn't it? So if t is equal to -1, x is equal to -1. What is y? When we are given y equal to t cubed minus t. We're also given y is t cubed minus t. So we replace t here by -1, we get 0, right? -1 cubed is -1, -1, so -1 plus 1 is 0. So we can also calculate dz dt at the point x, y, t equal to -1, 0, minus at the point x, y, at the point x, y, t equal to -1, 0, -1. Where is it? What is dz dt that we have found? We can use this. We can use dz dt in this form. Okay. You can also use dz dt in that form involving x, y, and t. So here we replace. Okay, let me write down it first. This is minus a half e to the power of y over 2 times 3t squared minus 1. And here we want to replace all xyt equal to -1, 0, -1. So if you substitute, you will get the same result. Okay? If you substitute, you will get the same result as previously, which is -2e minus 1. So this is the an example of the chain rule related to the first case, which I call it case A here. And of course, this can the case A, which was first related to a function of two variable xy, can also be extended, okay, to function xyz, where xyz in turns depends on t. Okay, then y as a whole is a function, w as a whole is a function of t. So we can calculate dw dt according to the same chain rule in case A, but we have to add another extra term here. W partial z times z partial t here. Let's see an example. Okay, before that, let me say something about common mistakes done by the student. Okay, some common mistakes when writing this chain rule. Some students, they write the chain rule in this form. Everything using straight D, which is not correct. Okay, which is not correct. Yeah, you see, some students, they instead of writing z partial x using curly D symbol, they write dz dx using straight D symbol here. Okay, similarly, instead of writing z partial y using curly D symbol, some students they write dz dy using straight D symbol. So this is the sometimes a common mistake committed by the student, and sometimes also student write it in this form. as z partial x times x partial t. Everything using partial derivative symbols here. So again, this is not correct because x and y are functions of a single variable t. So we need to write dx dt using straight d, not curly d here. So please make sure that you write this this chain rule using the using the right notation, right notation. Well, let's consider another example. Suppose you are given w equal to x cosine of y z squared, where x is sine of t, y equal to t squared, and z equal to e to the power of t. Okay, so this is w is a function of three variables x, y, z, where x, y, z are in turn in terms of functions t. So z w as a whole is a function of t, right? W as a whole is a function of t. You can see that clearly if I do the substitution. Sine t cosine, what is y, t squared, z squared is e to the power of 2t, right? If I do the substitution of x, y, z, you can see that this is a w as a function of t. Yeah. Of course, you can also calculate dw dt directly using a chain rule. Yeah. But we want to apply the partial derivatives, okay? It is easier to use the partial derivatives. So dw dt is, according to the chain rule, is w partial x times dx dt plus w partial y times dy dt plus w partial z times dz dt. Okay, what is w partial x? Anybody? I hope you are still with me. What is w partial x?
Cos xy
Cos
cos z cos y
y
z square.
z squared. Okay, that is correct. Dx dt is cosine t, right? Cosine t, yeah. And what about w partial y? Use the chain rule. The function is cosine. Y is inside the cosine function. So you need to differentiate the outer function cosine first to get what? Minus sine, isn't it? Minus x sine. First you differentiate cosine, you will get a minus sine. And then you differentiate the inner function yz squared with respect to y, which is what? Z squared, right? Z squared. And dy dt is equal to 2t. Yeah, 2t. And then what about w partial z? Again, z is inside the sine cosine function. So W partial z is minus x sine y z squared. Differentiate the inner function yz squared with respect to z is 2zy, isn't it? 2zy. Then finally, dz dt is e to the power of t. Yeah. Mm. Mm. So let's then we substitute y, x, y, z in terms of t. X is sine t, y is t squared, z is equal to e to the t. So we have here cosine. Let me write down cosine t first in front. Cosine of y, what is y? Y is t squared, and z squared is e to the power of 2t. Next we have 2t minus 2t. What is x? X is equal to sine t. We also have z squared. Z squared is e to the power of 2t, and then we have sine yz squared, which is t squared e to the power of 2t. Then finally we have minus 2xyz minus 2xyz sine t squared. We have t squared e to the t sine t, and then 2xyz. We also have another 2x. We have also have another t, so that means we have here sine e to the power of 2t, and then sine of yz squared is sine of t squared e to the power of 2t. I think we can leave the answer in that form. Yeah, this is correct. T squared. Okay, yeah. Is this correct? Next one is sine. Oh, we should have a sign here. Sine. Yeah. Okay. So this is one example that illustrates the case B of partial derivatives. We have two others, case C and case D here. I think I will discuss this tomorrow in our class. We have another lecture tomorrow. I think I will discuss the remaining two chain rule for partial derivatives here. You have any question? Any question? It seems pretty quiet.
So far, so good.
All right. I hope some of. What about this book? Have you ordered this book? Has any one of you ordered this book? Fill out the Google form.
Yes, Doctor.
Have you received it? Have you received the
yet.
order?
Not yet, sir.
Not yet.
Okay, I think it's good, for you to have that book, even though it is not compulsory. But I think it's good. I mean, if you have any other calculus book, it's also fine. But if you don't have any other calculus book and you wish to own a copy, you can buy this book, which I have suggested to you. It's also cheap, not so expensive. Yeah. So saya rasa setiap pelajar mesti ada kalau boleh satu buku lah untuk setiap course. So jadi you have your own mini library, you know. So for future reference, future use. Maybe some of you intend to intend to further your study to master's level or to PhD level. Or maybe some of you will go into this teaching line, you know, wish to be a lecturer. So I think it's good, you know, to have some sort like textbooks, you know, for your courses. Yeah. All right. So I will upload all the
Doctor.
lecture. Yes.
Can I ask when the book will be arrived?
Oh, I don't know.
Oh, okay.
Have you fill out the form?
Yeah.
Ah,
Yes, sir. We fill out the form
Ah.
and paid already.
okay.
Yes.
So
The form tu dekat WhatsApp ke dekat e-learning?
form tu dalam WhatsApp.
Oh, saya join group lambat, saya tak dapat link
Ah.
form tu.
Okay, nanti maybe somebody maybe can, you know, forward that again, right, in the WhatsApp group, that Google form. Yeah.
Doktor,
Boleh, boleh.
order kan?
Yeah.
Still boleh order kan?
Awak boleh order? Memang boleh order.
Maksud saya still boleh lagi kan order? Tak ada
Boleh. I think ada deadline ke?
Yes, it's 27th actually, right?
27. Kat mana dia tulis dalam pada Google Form gitu ke?
Yes.
In the Google Form itself, it is written there. Let me see. Are there any new information about deadline? I think the deadline here is 31st March. It has been extended to 31st March. Yeah. So you have time until 31st March to order. Okay. The book form.
Yeah, true. Due date 31st March.
Okay. Thank you. So before we stop, let me first show you your the QR code for your attendance.